or video whose goal is to find the nth term, what we're really doing is recognizing patterns and finding a general rule, or aka a function, for the nth term of the sequence. Now, we've actually already done this briefly, where we were trying to find something like a to the n equals 3n minus 17. And this function could work for any value of n. So you could say, okay, what is the 11th term of the function? You could just plug in 11 here and find the output value. So our goal is to find equations like this. And here are some strategies to do so. 1, something you've noticed already. We've looked for common differences. So for instance, my favorite pattern so far this entire unit, 2, 4, 6, 8, 10. This would be considered a common difference because we're either adding by 2 or subtracting by 2. You could look for a common ratio. So you could think of it as maybe 3, 6, 12. This pattern, you could either think of it as multiplying by 2 or going backwards, dividing by 2, which reminds me, it's good to write the note that multiplying by 1/2 is the same as dividing by 2. I know a lot of you know that, but it's always good in these sections to think of them as one and the same thing, because it'll help you find patterns more quickly. Also, sometimes it's useful to look at the numerator and denominator independently. For instance, you might end up with a function where the top of the function you are finding 3 to the x power, and the bottom of the function you are finding like 4 to the x minus 1. So you could have something that's exponential, but the real thing is that your numerator and denominator are 2 different patterns. And finally, something that happens is this idea of signs alternating. So if you have a pattern where every other number is positive then negative, if you assume that your first term is 1, if you think of taking -1 and raising it to the n power versus -1 and raising it to the n plus 1 power, if we plug in n equals 1, -1 to the first is a -1, which means this means that your first term would be negative. Versus, if you plugged 1 into this function, that would be -1 squared, which is a positive 1, which means if you use this in your function, it would help you say that the first term is positive. So these here, this here and this here will be helpful for you later if your signs are changing in your patterns. So we're going to relate back to this later. So if we want to find the nth term of these two sequences, and these two sequences I want to do at the same time, because if we look at the recursive first, I notice that this pattern is consistently going up by 1, and this pattern is consistently going up by 2. So recursive, remember, means that you're relying on the previous term. So if I want to find my next term, a to the n plus 1, you're going to take your previous term, a sub n, and add 1 in this situation. Here, for the recursive function, if I would like to find my next term, a sub n plus 1, I would take my previous term and add 2. So the recursive in both of these cases is not too bad. And there's a reason for these two that I asked you to find it first. Now, the explicit formula is more of a pain because we need to consider what term number we're on first, 1, 2, 3, 4. Then underneath, I write what numbers we actually have as outputs, 4, 5, 6, 7, 8. I'm going to do the same thing over here. 1, 2, 3, 4, 5. Outputs 1, 3, 5, 7, 9. And our goal for these is to figure out what am I doing to my input value to get my output? How am I manipulating this? How am I manipulating these input values to get these output values? Now, something that helps me is I noticed at the beginning of both of these problems that my common differences were consistent right away. So in this pattern, consistent by 1, this pattern consistently adding 2. Whenever these consistently happen right away, I know that these functions are going to be linear, which means that my explicit functions are going to look more like y equals mx plus b. So some of you might recall from an earlier video that these two numbers did come into play. We called these numbers the common differences, and they both ended up somewhat being slope. So let's try something. If I want to find my equation, and I take the first term and multiply it by 1. So if I take 1 times my first term, how do I get from here to here? Well, I need to add 3. If I take my second term and multiply it by 1, and if I add 3 again the same way, will I get here? Yes. If I take my third term, multiply it by 1, and add 3, will I end up getting here? Yes, I will. So to make this more general, I would take my n term, I would multiply it by 1, and then I would add 3. So to write this even better, my explicit function would be a to the n, or a sub n equals n plus 3. In the same way, this example, my common difference was 2 here in my recursive. So I wonder if this can act as a slope again, if I know that it's linear because of this pattern. So if I take my first term, 1, and I multiply that by 2, how do I get from 2 to what my output value should be? Well, I'd subtract 1. If I took 2 and multiplied it by my second term, would it still work? So if I have 2 times 2, I have 4. So to get to 3, I would subtract 1 again. If I take 2 and multiply it by my third term and subtract 1, would I get 5? Yes, I would. So if I want to make this more general, you would take 2 times whatever n term you're on and subtract 1. And no matter what, this should work. And you can check yourself. If I want to check 5, a sub 5 is 2 times 5 minus 1, which gets me 9. So I know I'm correct. So if you get a common difference, consistent pattern the first try, it has to be linear. I take a look at the pattern at the beginning. It looks like I'm going up by 3, 5, 7, and 9, which means that the next common differences would all be consistent. So my first common differences are, so it can't be linear, but if my second common differences are the same, that leads me to think that maybe my function has something to do with quadratic. Kind of an interesting pattern that I've noticed. So if I write n equals term number 1, 2, 3, 4, 5, and underneath I write the output values from the beginning, let's ask ourselves, how can I get from 1 to 1, from 2 to 4, from 3 to 9, from 4 to 16? If we're thinking quadratic, maybe our function is just taking the n value you're on and squaring it. Does it work? Is 1 squared 1? Is 2 squared 4? Is 3 squared 9? Yes, yes, and yes. So here's my explicit function. Yay for noticing patterns. This example, I noticed that we have signs switching off. So what I'm going to do is just ignore the signs for a minute. I'm just going to write 5, 10, 15, 20. And above that, I'm going to write n equals 1, 2, 3, 4. How do I get from 1 to 5? How do I get from 2 to 10? How do I get from 3 to 15 and 4 to 20? Each time I told myself that I am multiplying by 5. I take this term and multiply by 5, this term and multiply by 5. So I know in my equation I'm going to have 5 times n, or 5 times the term number I'm on. But we have to deal with this sign issue. So let me go back. We want the first term to be negative. So if I go back to that first page that we talked about, we had two situations where we would use this if the first term you want to be negative, and this if you want to be positive. So I'm going to use negative 1 to the n. So in front of this equation, I would have negative 1 to the n power times 5n. If again you want to make sure, let's check the third term. A sub 3 would be negative 1 to the third power times 5 times 3. That would get me negative 1 times 15, which is what we had originally. We wanted a negative 15. So this is correct. The next example I noticed again does have signs flipping off, or switching off, so that we will be dealing with a sign. But first I'm going to again just copy down the output values without signs, and above it I'm going to write n equals 1, 2, 3, 4. And if I look at these numbers in terms of pattern, I notice that we're going up by 3, 5, and 7. So the second differences are again consistent, which makes me think that I'm going to have some kind of quadratic function, which is helpful. So if I look at how do I get from 1 to 2, how do I get from 2 to 5, how do I get from 3 to 10? Well, if I squared 1, that would get me 1, not 2. If I squared 2, that would get me 4, not 5. I notice, though, these are 1 more than the squaring. If I squared 3, they get me 9, and if I did 9 plus 1, I'd get 10. So my function will probably have the term number I'm on squared plus 1. Does that work here too? So 4 squared, 16 plus 1, yes it does. But I do need to worry about the signs. This time we want our number to be positive in front, so you can take a look back at your notes if you'd like, but it should be -1 to the n plus 1 to make sure that your first sign is definitely positive. Last but not least, as soon as I see a fraction, I would suggest thinking about the denominator and the numerator separately. And above that, again, I'm going to write n equals 1, 2, 3, 4, just to help myself see something. Now, a sub n equals, I'm going to think about the denominator first, because when I look at the denominator, I notice that I have 3, 9, 27, 81. To me, that seems like 3 to the first, 3 to the second, 3 to the third, and 3 to the fourth. And I happen to be on the first. So what if I thought of it as 3 to the n? Hear me out. 3 to the first is 3, correct? 3 to the second is 9, 3 to the third is 27, and 3 to the fourth is 81. So this pattern looks appropriate for the denominator. In the numerator, because I'm thinking exponential here, maybe I'll think exponential here. So what if I have, this looks like 2 to the first, 2 to the second, 2 to the third, and this looks like 2 to the 0th. The problem is, it looks like 2 to the 0th is 1 less than the exponent that I have, and 2 to the third is 1 less than the exponent that I have. So instead of just 2 to the n, maybe it would be 2 to the n minus 1, because then I would have here, for instance, that would be 2 to the 1 minus 1, which would be 2 to the 0th, which would get me this. And then 2 to the 2 minus 1 would get me 2 to the first, which would get me this. Now, I would say that this type here is probably the hardest to see, because this definitely, noting exponential patterns, is much harder than some of this stuff, because here at least you have something to hold on to with this quadratic idea, but this is definitely a lot harder. So in class, we will make sure to have a lot of examples like these to make sure that you're practicing it enough, because in the video here, I've tried to show you sometimes when it's quadratic, what happens when the sign flips. Sometimes the functions are linear like this, and these patterns are nice, but unfortunately, sometimes we do just have to rely a little bit of guess and check in pattern recognition. So again, your teacher will have a lot of practice for you. If you have any questions about any of these, please make sure to ask your teacher tomorrow. All right, thanks again for sticking with me, guys. See you next time.